Hey everyone, welcome to this clinical briefing explainer. If you're an audiology student or a practicing clinician, you already know the human ear is incredibly complex. Sometimes the symptoms our patients describe just seem to, well, defy logic. Today, we're jumping right into some fascinating recent research. We're going to bridge the gap between those observable patient symptoms and the microscopic molecular mechanics of the cochlea, specifically looking at the brain's internal feedback loops. So here's our syllabus for today. We'll start with the hearing loss paradox, then map out the MOC efferent pathway, look at a really cool knockout mice experiment, evaluate brain states and amplification, and finally wrap up with the clinical implications. All right, let's kick things off with Section 1, the hearing loss paradox, specifically looking at recruitment and hyperacusis. As future audiologists, you're going to see this paradox all the time. You'll have hearing-impaired patients who struggle to hear a normal conversation, right? But then they literally wince in agony when a dish clinks in the sink. It's wild. And this perfectly highlights the difference between loudness recruitment and hyperacusis. Recruitment is a peripheral cochlear issue. When outer hair cells get damaged, low sounds aren't amplified, but loud sounds suddenly trigger this abnormally fast, massive growth in loudness perception. Hyperacusis, on the other hand, that's central. It's an extreme intolerance to regular everyday noise caused by a central or limbic maladaptation in the brain, bringing in fear and sound aversion. But how exactly does the brain tell the ear to make these central changes? That brings us to Section 2, the MOC efferent pathway, or brain-to-ear feedback. Okay, take a look at the anatomy of the medial olivocochlear, or MOC, efferent pathway. It's so interesting because it projects directly from the brainstem, the superior olivary complex, all the way down into the cochlea to synapse right onto the outer hair cells. Now, unlike afferent nervers that just send sound data up to the brain, this is a feedback loop. The brain is actually sending instructions back down to the ear. When these MOC neurons fire, they release acetylcholine that binds to alpha-9 and alpha-10 receptors on the outer hair cells and reduces their electromotility. So essentially, the brain has its own built-in volume dial it can turn down. Now we really need to contrast its short-term effects against its long-term role. For ages, researchers have debated what this pathway actually does in the short term. Is it helping with immediate attention? Does it mask background noise so you can focus on one voice at a party? The results there are super debated and highly variable. But on a long-term scale, we know for sure it plays a huge role in buffering acoustic trauma. The big million-dollar question, though, is does this pathway adjust cochlear gain, like the biological amplification of sound after chronic hearing loss? Let's find out in Section 3, the knockout mice experiment. To test this, researchers used VGLUT3 knockout mice. This is a genetic model with profound hearing loss. Why are they deaf? Because the upward afferent signal from the inner ear to the brain is totally severed. The synapse between the inner hair cell and the auditory nerve just doesn't work. So the brain is receiving zero acoustic information. Think about it. If the brain realizes it's completely in the dark and not getting any sound, what does it tell that descending MOC pathway to do? Well, look at these sensitivity curves mapped directly from the basilar membrane's vibrations. Focus on the VGLUT3 knockout mice. Paradoxically, these deafened mice showed a massive increase in cochlear amplification for low-intensity sounds compared to normal wild-type mice. The brain is literally turning up the gain. It's vibrating the inner ear structures more intensely, just desperately trying to amplify any faint signal it can find. But, how do we know for absolutely sure it's the MOC pathway turning that dial? Here's where it gets really clever. To prove it was the MOC pathway, researchers engineered a dual knockout. They took those deaf mice and also deleted the alpha-9 receptor on the outer hair cells. By removing that efferent receptor, they basically snipped the downward wire from the brain. And check out the result. It completely blocked the amplified gain. The sensitivity curves dropped right back to normal. This is our smoking gun. It proves the MOC efferent pathway is directly responsible for cranking up cochlear amplification when hearing is lost. Let's move on to Section 4, brain states and amplification. Is this process dynamic or static? We really have to ask ourselves, does a patient's moment-to-moment brain state, like their immediate attention, stress, or arousal, acutely change this amplification? Like, if the brain controls the volume knob, is it constantly twisting it back and forth every few seconds based on whether the subject is alert or relaxed? To answer this, the researchers tracked the brain states of awake mice using pupillometry. Just like our pupils dilate when we're stressed or super alert, mouse pupils do the exact same thing, giving us a real-time window into their neuromodulatory state. So, they tracked these spontaneous pupil changes while measuring cochlear vibrations. And guess what? They found absolutely no acute impact on the cochlea. Fluctuations in arousal did not dynamically alter cochlear amplification at all. This is huge because it confirms that this MOC modulation is strictly a chronic, long-term adaptation to hearing loss, not some rapid, state-dependent volume knob. So, what does this all mean for us? Section 5, clinical implications for patients, specifically focusing on tinnitus and hyperacusis. Let's zoom back out to the clinic. This significant statement neatly ties all our detective work together. It links that chronic upregulation of the cochlear amplifier directly back to your patient's most frustrating complaints. When a patient gets age-related or noise-induced hearing loss, they lose afferent signals. Their brain realizes it's missing input, so over a long stretch of time, it uses the MOC pathway to just chronically crank up the physical gain in the cochlea. As this quote beautifully summarizes, the irony here is that the brain is genuinely just trying to help. It's trying to partially compensate for the hearing loss. But by chronically boosting that gain to make up for the diminished input, the whole system becomes hypersensitive. It's like the physiological dial is stuck on maximum. And this exact mechanism likely contributes heavily to the agonizing symptoms of tinnitus, that ringing caused by overactive amplification, and hyperacusis, where regular everyday sounds are amplified to painful levels. The biological cure the body attempts is actually creating the very symptoms the patient complains about. I want to leave you with a rather provocative thought to wrap up this explainer. That VGLUT3 protein we talked about, it's not just in the ear. It's heavily present in neuromodulatory brain structures and is strongly linked to stress and anxiety. And we know from huge public health studies that stress and anxiety are heavily associated with hearing loss symptoms. So if this MOC pathway is a descending brain-to-ear circuit, could treating a patient's chronic anxiety actually lower this biological feedback loop? Could holistic psychological care literally dial down their physical cochlear gain and silence their hyperacusis? It's wild to think about, but it completely changes how we might view comprehensive audiology care. Keep that in mind the next time you're sitting across from a patient.